Hi guys, this is worksheet number 7, magnetic flux, Faraday's, and EMF. So what is magnetic flux? So we have this equation that I equals BA cosine theta, right? So it's basically a magnetic field that's penetrating a loop with a certain area. So that's what the area there is. B within magnetic flux is constant. And this is a dot product. So that means the angle theta will be the angle between B and the A vector. So the A vector will be perpendicular to it. So in most cases, and unless kind of otherwise stated, it'll be equal to, we'll be able to just be B times A. So Faraday's law tells us that a change in magnetic flux results in a change in the induced voltage. So there's a few ways to create an induced voltage, right? And that by that I mean like a change in flux. You can either adjust the magnetic field strength, so it'd be like decrease or increase B. You can change the area, or you can alter the orientation of the loop such that, if it was previously, standing straight up, you could rotate it on its side, and that must be between like 0 and 90 degrees. So it'd be like rotating such that the B field going through it adjusts. And then Lenz's law, this is where it always gets kind of tricky. So I'll read the definition and I'll finish going through all these other equations, and then I'll kind of tell you about the way I think about Lenz's law. So with Lenz's law, the induced current flows in the direction that produces a magnetic field that opposes the change in magnetic flux. So basically, whatever it was, you're like increasing in. To oppose that, you're gonna need to increase the amount going out. So like more field going in to like through Lenz's law, you're gonna want more out. And within each of those, the induced current flows in the direction that that produces a magnetic field that would oppose said change, right? So again, in the case where we're saying like more is coming in, when you do more coming out. And when you do more coming out, you'll see that it's a counterclockwise induced current. And you can either think about it logically, or what I did is I just memorized a table that wrote everything down for me. So I feel like that way is the foolproof way. But you can do whichever one you want. And then with this EMF equation, we can use this equation when there's an increasing or decreasing magnetic flux, and it must be in the shape of a rectangular square. So B, L, and V are mutually perpendicular. That means the way the field's going, the length of the side, and V are all have 90 degrees between each other. So in those cases, you'll normally have like a square loop moving through a magnetic field. And you can imagine that like it's flat on the I don't know, on the surface. The field is going in or out of it, and it's moving along that horizontal axis. And then RLC, there's a summary of equations. We'll go through each of them. But the important thing is that like what's impedance? That's just the total resistance of the circuit. And it accounts for that by including the inductive and the capacitive reactance. And then there's the phase angle. Actually, I don't even want to go into that. Because you don't need to worry about it. And okay, we can just move on to like kind of the rules I like to do with Lenz's law. So instead of writing increased and decreased every single time, I'm just going to write I and D. So what I like to think about is like if I increase the amount going in, like, right, so that's how much field's going in. So I in, then by Lenz's law, you're going to need to increase the amount going out. Okay. And whenever you see the word out in the second part of this, that tells you it's going to be counterclockwise. Okay? Yeah. Oh, thank you. Wow, you guys were just going to let me talk this whole time. Is that too dark? Yeah, it's too dark. Is there no in between? Okay. Okay, so when we increase I in, we're going to need to oppose that by I out. And whenever we see the word out here, that means counterclockwise. So that's like scenario number 1 that exists. The other one is if you decrease the amount going in, you're going to need to have more going in. So decreased in, more in. And whenever you see in this second part right here, it's going to be a clockwise induced current. Maybe I should say clockwise I induced. I induced. And then third scenario, if you have increase out, you're going to need to have more in. Again, we see in right here, so that tells us clockwise I induced. And the kind of the last option this could be is if you decrease the amount going out, to oppose that by Lenz's law, you're going to want to have increased amount going out. What's important to note here is like with this decreased amount going out and then increased amount going out, it's about maintaining a balance, right? Okay. And again, we see out here, so that means counterclockwise, I induced. Okay, so again, like kind of to illustrate this point, I think it's good to like see an example here. So let's consider the following, right? So if you increase the amount of field going in, so let's say increase B in, what do we need to do to maintain this balance? We increase in, we need to have increased out. So I'll say increased out. And because we see out here, therefore the induced current is counterclockwise. That's like how my brain thinks about it. And I think that doing it this way is just kind of the surefire way to do it. All right, I'll pause and take questions. Oh. Okay, so number one, I'm pretty sure this is from a homework. I don't know if it's from this homework, but I just think that it's such good practice. If I didn't do this, it'd be like a blunder to skip this. And I think that it'd be good if we all took a chance to try each one out. So I'll pause the recording and then just ask people. Okay, so in this scenario one, we have this loop here. We have a wire and we know the direction of current right here, and we know it's increasing. So I is increasing. Okay, so if we do a right-hand rule right now, we can determine the direction that the field is pointing, right? So you're gonna put your thumb on the wire, curl it, and on this side, and within the circle, we have a B field that's pointing out, right? I is increasing. What effect does that have on the field? That means it's increasing, right? And now I go back to my little chart I like to draw. So I have more going out, so I'm increasing going out, then I need to increase going in. So I will have a clockwise current, induced current. So my I induced is going clockwise. I'll call this one A. Okay, and now in this scenario here, we have like this loop, this magnet right here, and we know that the field coming off a magnet is like, it's like this, right? And it's getting closer, so that means we are now increasing the amount going out of the loop. So to maintain Lenz's law, we need to increase the amount going into the loop. Increase in, that means clockwise induced current. So again, it's clockwise. C here is kind of the, it's similar to actually what we just did, where we now have a loop moving away from this magnet. And that means we have the field going this way, and we're moving it away. So that means we're going to be having, we're going to have a decreasing amount going in. So that means we have to have an increased amount going in, again, clockwise induced current. For part D here, kind of the same as part A, we do our right-hand rule, it's going into the page. So within here, it's going into the page, it's decreasing. So that means we are having, we are decreasing the amount in, we need to increase the amount in clockwise. So it looks like everything's coming out clockwise here. And then part E, we have a rectangle. And this rectangle loop is entering a field that has a bunch of, entering a region with the B field pointing out of the page. So you can imagine as this loop enters more and more, we're going to be increasing the amount going out of the page. So that means we need to maintain balance by having an increase going in, again, clockwise induced current. And then finally, this is kind of, again, similar. where now we have this rectangle exiting this field where the field is pointing out of the page, something like this. So that means we're going to be having, we're going to be decreasing the amount going, decreasing the amount going out. So we need to increase the amount going out, and this one will be counterclockwise. Oh, I wrote counterclockwise. I meant I induced. So here we have a wire in question 2 that consists of 20 turns with an area that's given. We know the total resistance is 5 ohms, and there's a perpendicular magnetic field going into the page that's passing through the coil. And the magnetic field has an initial magnitude of that value. We know at the time 0 seconds, and then after it increases over time to 0.6. And we want to determine the value and direction of the induced current. Okay, so when does an induced EMF exist? Well, that's when there's a change in B. So here we have an obvious change in B over time. And part A of this, or what we're asked to do now, is find the value and direction of the induced current. So the equation we're going to use is that induced EMF is going to be equal to minus the number of loops that delta I naught B, and divided by a change in time. So we know what this this value is that's given on the equation sheet. Well, that's going to be equal to the change in B times its area and the cosine of the angle between them. So minus n delta BA cosine theta. And that angle theta now is the angle between the area vector and the field. Well, it's 0 degrees because it's like going into the page, and then it's also pointing down. So cosine 0 is equal to 1, so we don't really need to worry about that. And then delta t we can plug in a sec. I like to factor out what isn't experiencing a change, right? So the number of loops is constant, the area is constant, but what is changing is the field over time. You now have to plug in, the change in field over time, where, let me write it real quick, BF minus B naught divided by delta T. And you'll end up solving for the induced EMF as minus 0.165 volts. Okay, so because the induced EMF is negative, we want to make the flux opposite that the B is pointing. And here we want to oppose the amount that's going in. So the opposite of in is out. So we need to have more out. And that more out is indication for counterclockwise induced current. So I induce is counterclockwise. Okay. I should move this. Okay. In question 3 here, part of the rectangular loop with the wire with those dimensions is situated inside the region of the uniform magnetic field of 0.55 T. The total resistance of the loop is given. Calculate the force required to pull the loop from the field to the right at a constant velocity. Okay, what does constant velocity tell us? Yeah, so that means when we set up our expression for F equals ma, we know that A is equal to 0. And what are our forces acting here? Well, we have the situation where, well, let me quickly draw. All right, that was horrible. We have a force going this way. We want to oppose it with a force going this way. And and the other thing that we're given are our dimensions here. Okay, so again, the forces we can define using a coordinate system, and this is not something we're used to. So F is equal to FB minus FB, which is equal to 0. And we can solve now for the amount of force that we'll need for to equal the force being pulled to the right using the following equation, where we know the I induced L B sine theta. And again, the sine theta is equal to 90, so it's just 1. And the equation for I induced here will be equal to the induced EMF divided by R, which is given, times LB. Induced EMF is equal to BLV divided by R. Now remember, this is that special equation I was talking about that we use when we have a square or rectangle moving through a field. The important thing here is that it actually I'll explain that on the down the road. I think it'll be easier to visualize it down the road. Okay, and if we clean this up a little bit more, we'll see that it's B squared L squared V over R. You know, your force comes up to be 0.5 newtons, and we know the direction we're acting. Okay, and I don't think they ask you, but if you were to like ask which way the induced current goes, which way would it go? Yeah, it is clockwise. So as you get it more pushed to the left, you're gonna have an increasing area within the field, and that means the amount of B field going in is going to increase. With increased in, you're going to want to have increased out to maintain that balance by Lenz's law, and that's consistent with counterclockwise. So the current induced current going through the loop there would be clockwise. And then the last example is one of my favorite ones here to do, because I think if it's on when it's on the exam, and it does come up, I'd say like every other year it seems to come up, is these LRC circuits, and it's just free money. All you have to do is know how to plug in everything. So you're given all these variables, right? We know what R is, C, L, frequency, and V naught. We need to first determine the total impedance A. And again, remember, that's the resistance of everything. So here we have a capacitor, an inductor, and a resistor. All of those have resistances. And to like find the sum of the resistances, we need to solve for Z. And how do we solve for Z? Well, Z is equal to the square root of R squared plus XL minus XC squared. Okay. And again, those are those impedance values relative to the capacitance or the inductance. Well, you need to solve for XL, which can be solved as 2 pi FL. In this case, 2 pi 50 times 0.18, which is equal to 56.6 ohms. And then you can solve for XC, which is going to be equal to 1 over 2 pi FC. And that's going to be equal to 39.8 ohms. See how everything's in units of ohms. So we know when we eventually plug everything in, including that R, which is equal to 200, and then these two into their respective positions, we're going to come up with a total resistance value, which in this case is equal to 200 ohms. Sometimes they don't ask this question, though, as nicely as I've given it here, where you are asked to solve for impedance and the next thing and then the next thing. So if you'll see that there's really stepwise way of doing this where you can only solve for things knowing the previous. So like, for instance, we want to determine I naught or I max, right? How do we solve for I max? Well, I max is an expression of V max over Z, right? So you need to know Z to solve for it. And now you just plug in, I max comes out to be equal to 0.24 amps. And the next one, we're asked to solve for the peak voltage across each element, okay? So the peak voltage across each element. So what is that is the V max against through the resistor. That's going to be equal to I max times R. That's going to also be equal to the max through the inductor. Again, that's I max times that XL, and then V max through the capacitor. That's going to be I max, and then the inductance of, and then the XC. Okay. And we know what I max is. We just solved for that before. And we already know what R is. We solve for XL and XC. Each of these expressions come out as follows. So that's 48 volts. This is equal to 13.6 volts. and this is equal to 9.6 volts. And then we have phase angle. So phase angle has two components, and kind of what I was talking about in the beginning. I don't even know if it comes up, but I'd rather just say it and not need it than not say it and we do need it. So depending on if your phase angle is positive or negative, those tell you if the current's behavior relative to the voltage. So a positive means that your current lags behind the voltage, and then a negative means your current leads ahead of the voltage. So what the heck does that mean? Well, in the case that your current is lagging behind the voltage, that means your current reaches the max value after Vmax is reached. And alternatively, if your current is leading the voltage, your current will reach max before the voltage reaches its max. So they didn't ask us to solve for it on this one, but just know that that can come up. So this phase angle is equal to XL minus XC divided by R. And at this point, we should know how to rearrange these kind of things. And we can see this. It comes out as a positive, wherever that's worth. And then finally, P average. So P average, again, this is another equation we'll know, is equal to I RMS, which should look familiar, times the resistance. And we know RMS equation to the max value, I max, is I max divided by root 2 is equal to I RMS. So we know what to plug in for P average, which is equal to I max divided by root 2, square root that whole guy, times R. P average is equal to 5.76 watts. Okay, so this is kind of what I mean where I gave you the question kind of nicely. You solve for Z first, and then with Z, you can solve for I max. And with I max, you can solve for each of these values. You can solve for your phase angle, and then you can solve for your P average. But this same methodology applies if they said, what is the P average from the beginning? So you should kind of remember that when you see these conditions where you have this LRC circuit, you need to find some average power dissipated. You need to find a phase angle, something that you will get downstream of this initial impedance value. Use this methodology, and it just sticks true every single time. And here in the drawing, I guess I didn't even say it, this is an AC circuit. So that means it's like alternating voltage or current. And that means it can like change over time, and it can actually reverse direction too. But I don't even know if that's for the people at home who want to know. All right, I'm gonna stop the recording and take questions.